is, if this is what a decision tree is, then what can it and it cannot, and what can it not represent? Like, for example, if you handle continuous attributes this way, can you learn any frontier between positive and negative examples? Right, here's the question, right? Let's, like, here's a little diagram, right? Let's suppose that, my positive examples are like this, right? Here's a bunch of positive examples, and here's a bunch of negative examples, right? Can you learn this with a decision tree, the way I just described? Yes or no? Yes, because?
Because you would cover the universe of values.
I'm not sure what you mean by covering the universe. Tell me what the frontier would look like here, right? What would it look like? Actually, before we even think about decision trees, what is the frontier that you would put here to separate the positive from the negative examples?
Correct.
Yeah, exactly. It's just a line like this, right? Hey, we can do this by eye. Like, one famous person in data mining said, if people could see in high dimensions, we wouldn't need data mining. Right? So here, we don't need an algorithm to figure this one out. Right? So here's this straight line. Another question is, can I learn this straight line with a decision tree?
Could approximate it if you had a lot of branches.
Very good. I can approximate it, but I cannot learn it. Why can I not learn it exactly?
It will not fit into any equation or something.
Well, because a decision tree partitions by like horizontal and vertical lines.
Exactly. Let's say this is x and this is y, right? All I'm allowing myself is tests of the form x greater than something and y greater than something, right? X greater than something are splits like this, right? Y greater than something are splits like this. So you can only form axis parallel frontiers. So you can't learn this. Of course, given enough data, you could approximate this with a tiny little staircase, right? But this is not very satisfying because now you have a really complicated decision tree. In fact, the complexity will go off to infinity as you get more data, when in fact a much simpler thing would suffice. Okay? So in principle, you can approximate anything with decision trees, but in practice, many things you cannot approximate very well. However, you can still learn good decision trees in a lot of domains because we're almost never in this situation. Because the space is very high dimensional, it's not just two dimensionals, the data is very, very sparse. So we have no idea exactly where the frontiers lie, so doing axis parallel cuts will actually be good enough most of the time. Okay? And it can also be done much more efficiently than, say, fitting a big complicated equation at each node of the decision tree. Okay? Yep?
Is there any way you could learn the threshold values in a decision tree?
No, absolutely. This is what we want to do. We don't know where the thresholds are going to be. We need to figure out where we should put them. So here's an example, right? Here's a decision tree that tests, two continuous variables x1 and x2. For example, if x2 is less than 3, then we text x1, and if x1 is greater than 4, then we have a 1. Okay. So what is x2 less than 3 and x1 less than 4, right? It's this square over here, okay? So in this square over here, we predict 0. Okay, everybody agree? And so on. If on the other hand, x1 was greater than 4, then now we're in this sector, right? And so you see that each of these rectangles corresponds to one of the leaves in the decision tree that we have here, okay? And with a lot of data, we can draw a very fine set of rectangles, right? This is one of those Mondrian paintings, right? We can have very fine little squares, but they're always going to be squares, or hyperrectangles is the technical term, right? Because this is going to be in hyperspace, in high dimensions. Okay. Any questions? Yeah? Okay, so next question. So this was for continuous variables, right? For continuous variables, we saw that decision trees can approximate things, but not necessarily learn them exactly, right? What about discrete functions? So to simplify, let's suppose we're just trying to learn a Boolean function of Boolean inputs. Can we learn any Boolean function of Boolean inputs, or can we only learn some of them? What do you think? Are there some Boolean functions that we cannot represent with a decision tree? And if so, can you give an example? What is your feeling? Remember, you have to get lucky. Do you feel lucky today? Mm-hmm.
Feels like you should be able to, right? Feels like you should be able to.
Yeah. Why does it feel like you should be able to?
In the tree, you could basically describe the same Boolean function in the tree. You know?
Right, right. So think about this, right? You can describe any Boolean function using a truth table, right? That's what it is at bottom, right? It's a truth table, right? So now the question is, if I give you a truth table, right? Any truth table in the world, can you turn that into a decision tree? Or not?
Yes.
Yes, because somebody at Microsoft said yes. Yeah.
Worst case, you've got as many branch points as you've got rows in your truth table. So you
Exactly. Exactly. How about this? I don't actually have that example here. But let's draw that example actually. Here's my truth table, right? Let's say I'm testing variables, x1, x2, etc., right? And then here I have my answer, my y, right? And for each combination of these values, I have a value of y, right? So how about we do this, right? Let's not worry about how large the decision tree is going to be, right? We're just going to worry about finding one, right? First we test x1, right? x1 is like 0, 0, 0, 0, and then 1, 1, 1, 1, right? So if x1 is 0, then we know we're in the upper half, right? If x1 is 1, we're in the lower half. And now you can already see what's going to happen, right? Now we test x2, 0, 0, 1, 1. Well, this split things further. So in the worst case, what has to happen is that I have to test every value of every variable in each branch, and I'm going to have 2 to the n of these, but that's okay, right? That's a decision tree. Okay? So clearly we can represent any discrete function with a decision tree. Okay? Whether or not we can represent it efficiently is another question, a very important one, but we'll defer that until later. And we'll also ask ourselves, are there more compact ways of doing this than decision trees? Okay. Questions? Okay, very good. So decision trees are actually a pretty general method. And clearly they're also variable-sized hypothesis space, right? Because if you think, for example, of decision trees of depth 1, also known as decision stumps, right? These are decision trees that basically just test one variable. And if the class just depends on one variable, I can represent that with a decision tree of depth 1. If I go to depth 2, now that actually includes all models in, over 2 variables, all Boolean functions over 2 variables, and also some Boolean functions over 3 variables, right? Like, for example, I could have a function like this, x1 and x2, or not x1 and not x3 as a decision tree with 2 levels, right? Because in the first level, I would test x1, and then in the second level, in one case, I would test x2, and in the other case, I would test x3. Okay? Very good. So